Hey, BCalc students. Wanted to give you a little review in case you missed this on when we were going over this in class. It was just a quick summary of a couple things with limits and especially with L'Hopital's rule. So I just want to do a very short little summary here of when we did limits way back in August and September, and then a brief adjustment here with L'Hopital. So in case you missed class or maybe you weren't taking very good notes that day. So going back to the fall, if you remember, we had three basic types of limits, and we started with a limit where we would say, what if you took the limit, for example, as x approached 2 of x cubed plus 1? And we would say, if you had this kind of a limit, we would say, well, these were Nike limits. And we called them Nike limits, and we say, you just do it. You just go ahead and put in the x value. Because the limit's a y value, remember. I'm actually going to put that at the very top. Limits, and my slang lingo here is y value. So every teacher kind of has their little Andersonisms, like Miss May says a y value approach. We're all, basically the same. So the limit is x approaches 2. Well, the y value here is 2 cubed plus 1 is just going to be 9, and you just do it. Well, this virtually never happens. We don't have those kinds of limits for a reason. But that was the most basic kind. The two types of limits we had were when you had the limit, and we would say as x approaches 2, and what if we had something like x squared minus 4 over x minus 2, and I'm going to contrast that with what if we had the limit as x approaches 2 of, let's say we had x plus 1 over x minus 2. Well, in this situation, you always try a Nike limit if you can, and if you put 2 in there, you wind up with getting, you get 0 over 0, and earlier in the year, we used an AP Calc AB shortcut where we'd say, well, this is going to be a hole or removable discontinuity. And this is an AB shortcut that I do want to warn you, in the future, things get a little more sophisticated than this, but with L'Hopital's rule, you're not going to have to worry about it. But we would get a hole, and we had 4 strategies on how to solve this. And if you remember our 4 strategies, the first one we had, you could factor and get this to work. Another thing we would do is we would multiply by conjugates. That would sometimes work. The third thing, we would get a common denominator. The fourth thing we did is we would hack with a calculator. If you remember, we'd use a T-chart and we'd actually do this. But for this particular one, it was factoring worked, and you would say, well, it's really the limit as x approaches 2, and the top turns into x plus 2, x minus 2, using the factoring strategy, and the bottom was still x minus 2. Well, these cancel. I put in the 2, and it looks like the answer is 4. So the y values you approach to is 4. Now, this is discontinuous, and if we were to sketch the graph of this one, you literally have a hole in the graph at 4, and the graph would look something like this. And if you have the settings on your calculator correct, you can actually see your calculator actually give you a hole in the graph. Okay, and this is what we were doing. We were reconciling what is the y value being approached, and this was a very important skill. It was very, very powerful later. And this was but this was the removable discontinuity, or the holes. Well, then the third type we had was when you put in the 2, and you would put in the 2, and in this case you would get 3 over 0. And we generalize this to what happens when you get a number over 0. Well, when you get a number over 0, you know you have a vertical asymptote. And you already know the answer does not exist, because we're looking for y values, and your y value is either going to be positive infinity or negative infinity. So we know the answer does not exist, but we have to clarify. So the y value, we're going to say this, the solution is DNE. But we need to clarify. And the way we would clarify, we could graph them, and so we'll actually just do this one. So as we were approaching negative 2, I'm going to actually want to just graph that one. The graph, what it looks like is, at positive 2, we would have a vertical asymptote. And if we use our shortcuts from Algebra 2, top heavy, bottom heavy equal, these are equal, and I would have a horizontal asymptote at 1. Okay, and x and y. Okay, and if you want, you could make a t-chart to help yourself out, which was a strategy we would use. And we would say, well, it looks like when we get to 2, we get a vertical asymptote. But when we approach 2, like from the left side, we get one of the infinities. Because asymptotic behavior, we know we're going to one of the infinities. We just don't know which one. And so this is not a minus sign. It's a fraction bar. So which one of the infinities am I going to? Well, if I put 1.9 into the numerator, it's going to be a positive number. If I put it into the denominator, I'll have a negative number. So I must have been going to negative infinity. And in fact, if you put in 0, you'd be negative half, but you get this kind of behavior. As I approach 2, from the left side, I'm going to negative infinity. Now on the right side, the 2.1 side, I get positive over a positive, I would be getting this. And so we would call this, although it does not exist, we would say this is split behavior. And we would say that this disagrees, or this does not exist, it disagrees on the infinities. Now, just for the sake of time, I'm not going to do all of them with a numerical example, but we also could have had this behavior. Let's make that a little more level here. We could have had this behavior. We still could have had this at 2, but maybe when we did our test, we would have had this. They would have agreed on infinity. Well, my conclusion still would have been does not exist, but I would have said, however, this agrees on positive infinity. Whereas and we would call this a volcano, by the way. Volcano graphs. On the split, by the way, I do want to clarify this one was DNE, does not exist, combined with it disagrees on infinity. Okay? And by the way, because the reason we know that this does not exist is that infinity is involved. Infinity is not finite, so the limit does not exist. There is another reason limits don't exist, and that's to do with agreement. We'll do that one later. Okay, and then the last one, potentially you could have had the tornado graph, where maybe this thing would have had this behavior, and they would have agreed on negative infinity, but it still does not exist. Does not exist, agrees on negative infinity, and we would call that the tornado graph. Okay, but again, you always just check, see if you have limits, and the nice shortcut is you always try to make it a Nike limit. If it doesn't work, you have a hole, you use your strategies, it's number over 0, you know it's one of the asymptote type things, and that's what you have. Now, just as a little asterisk down here, the other situation where limits do not exist, it works better when you have a picture. So the other thing would be, I'm going to draw this picture. So what if I had a function that came up, and this was my graph, okay? And I'll just call that 3. Call this y value 4, and I'll call that y value 6, okay? Because if you recall, there's two reasons limits don't exist. Infinity is involved, and the other one is disagreement. And so for this one, if I said, find the limit as x approaches 3 from the left, find the limit as x approaches 3 from the right, and then if you just ask, what's the limit as x approaches 3, it's implied you're coming from both sides. So if we approach it from the left, as we approach 3 from the left, it sure looks like we're going to 4. If we approach it from the right, we're going to 6. As we approach 3 from both sides, we have disagreement here. So we just say does not exist because of disagreement. Okay? Very quick limit review. Well then, what wound up happening here, very late in the year here, we went over this new little rule here. And this new little rule has to do with actually removable discontinuity. And it's a special little rule that goes with this. So this used to be in BC, and a few years back they moved it into AP. And so I'm going to give you what if you, when you take the limit as x approaches, and I'm just going to put a c value, okay, of a function, what's going to happen if you get what is called, and now we have this new term, what if it is called indeterminate? Now these are a lot of fun, and if you have a math brain, I love playing around with infinity because it's just fun, and it's sometimes it can surprise you, the results, but indeterminate form is just sort of it's fun, it's a little bit mysterious, kind of puzzly, and it's just fun to play around with. And so indeterminate form is one of those things. Now, there are 7 types of indeterminate form. The 2 that we use in AB, and actually almost the one we use exclusively, once again, let me write this down here. There are 7 types of indeterminate, but the 2 we have to worry about is 0 over 0, and when we have infinity over infinity. Okay? Now, almost every time it's going to be 0 over 0. So the reason we don't like to show this till the very end of the year is because if we show it to you when you're doing this, you go to this shortcut and you don't learn all of the nuance that is very important to understand about disk removal, discontinuity, and limits. So when you get what's called indeterminate form, you get to use this new property by L'Hopital, and it looks like L apostrophe hospitals. So this is called L'Hopital's rule. And what L'Hopital discovered was that if you have indeterminate form, so I'm just going to make it really, I'm going to use some slang here. If you have indeterminate form, in the form that we're using, indeterminate form, for example, if you have the limit as x approaches c, and my numerator is a function, and my denominator is a function, okay? If I get indeterminate form, okay, then, and I'm just going to put indeterminate, okay? If my limit, as I try to do a Nike limit, if I get indeterminate, then give this a shot. Then take the limit as x approaches c, and just take the derivative of the top over the derivative of the bottom, and try it again. Okay? If that doesn't work, do it again. And so it's a cool little shortcut. In fact, I'm going to show you back with this example. I barely have enough room here to do this. I'm going to actually do this one here with L'Hopital's rule, and let's see if we get a 4. Okay? I'm going to sneak that in right down here. So I'm going to recopy this one from the original question. We'll use L'Hopital's, and I'll show you how slick it is. Okay, so let's pretend we have the limit as x approaches 2, and I'm going to do this again, x squared minus 4 over x minus 2. Now you try to make it a Nike limit, and you get 0 over 0. Now, instead of doing our strategies, you just go, oh, I'm just going to, the slang we say L-hop it. Just L-hop it, and just say, okay, make a comma. Well, now let's do it again, but we'll take the derivatives. So it's the limit as x approaches 2. Derivative of the top is 2x. The derivative of the bottom is 1, and we just made it a Nike limit. Take the limit as x approaches 2, and you get 4. Okay, and everybody always loves this, and you're like, oh, wow, that makes these way easier. So what you've probably noticed is in some of the FRQs, they'll sneak in a limit question, and frequently they're just kind of testing on L'Hopital's rule. And maybe there'd be like one multiple choice if you were taking that portion of the test. Okay, so that's just a brief little limit review and a little thing on L'Hopital's rule. Okay. The next thing I wanted to go over was the next piece that we went over that was really important was derivatives, and I wanted to just go over one graph that applies limits to that. And so we're going to take a look at that. So I'm going to take this screen, or take this away, and we will look at our next board. And so the next thing I wanted to go over was the key graph that goes with taking derivatives. And we did this little evolution that came up. But I'm just going to jump to the main graph that we get here, and this was a really important thing here. Oh, terrible. Got to draw a straight line here. This is always the great part about AP Review, is that you get to tie in things and revisit stuff from earlier in the year. So what I want you to pretend here is we're going to take a function, and we will call that f, and there is x, and here is the y-axis here. Okay, and just a little bit longer. And I'm going to take an interval here. And if you, in fact, I think maybe I'll just erase it. So we said earlier in the year, we said, well, and you guys did this at the board, we said x sub 1, and I called that x sub 2. And I called this y sub 2. And I said I would like to know what is the slope of that line. And we talked about how this was actually a secant based on actually what you learned in geometry. And we would say, oh, well, the slope of that secant is equal to, we've all passed Algebra 1, it's the difference in the y values over the difference in the x values. No big deal. We did that, and then we said, okay, that was y sub 1. And then I had you guys do this at the board literally. You would go up and I'd say, okay, now let's just write this in function notation. So, can you, instead of using y's, can you use this as f of x sub 1 and make that f of x sub 2? And we would say, okay. So, whoops, the only thing different here is f of x sub 2 minus f of x sub 1. Okay, no big deal. And then I said, okay, well now what we're going to do is instead of making that sub 1 and sub 2, we are going to call the distance between our x values, we're going to use fancy pants notation called delta x. And so this value right here is going to be x plus delta x. And now up here, these get to be a little bit different. And this y value right here is just f of x, and this one up here will be f of x plus delta x. Now, make a little adjustment on your slope formula. And we say now the slope of the secant is equal to f of x plus delta x minus f of x. Okay, so there's the slope of the secant, all fancy pants notation, everything's great. We're still in Algebra 1, we just have nice fancy notation. Okay, then if you recall, I would have somebody come to the board and I'd say, well, I actually don't want to know the slope of the secant, I would like to know the slope of this tangent right here. Okay, and the interesting thing about tangents is a point of tangency, you only get 1 point. Secants, you get an interval, you get 2 points. And so we have, I just want to know slope at 1 point. And so I said, so I'm just going to use this slope of the secant. How close is the slope of the secant to the slope of the tangent? You can see they're both positive, but they're kind of far apart. And I believe I said, I know you've been told this since Algebra 1 that it takes 2 points to calculate slope, but why don't you just use the same point twice? So what if I just said, you know what, the slope of the tangent, and let's just use the same point. So the difference in x over, or the difference in y over the difference in x gives me 0 over 0, which is undefined, it didn't work. So there's clearly an answer there. It looks like maybe a slope of 2, so I can't use the same point twice, that doesn't work. So I said, I don't know, I'm sick of playing with this, I'm just going to do this. I'm going to pick another point on the function, and I'm going to do that. I don't know, maybe it's close enough it'll work. And then as you guys, various people came up to the board and they picked a point that was closer. And you would pick a point that was closer and a point that was closer, and what you were starting, or what you were hopefully noticing, is that every time you picked a point that was closer, the delta x value was getting smaller. And x plus delta x, I mean, this was approaching this right here, or you could say the delta x value was approaching 0, and we would play this game till we got super close, and then we just said, well, since we know how to do limits, what if we just said the slope of the tangent was this? What if we just said, let's keep this thing, f of x plus delta x minus f of x, and the bottom here, oh, I'm sorry, and back over here when we changed our denominator here, if you guys remember, we had x plus delta x minus x, so our denominator just turned into delta x. And we said, well, what if we just throw a limit statement in front of this? And we say the limit as delta x approached 0. That could be the tangent. So all we're doing is letting delta x, which is the difference between these two things, delta x is becoming 0. So eventually this will be the same point. Because if you try to put delta x in here, you put delta x in here again, you're going to get 0 over 0. So we could approach it. Maybe we could use all of our skills with figure out limits to actually get the value. And that's what we did. And the reason this became so important is you need limits to figure out instantaneous rate of change. And so what this thing is right here, This is the formal definition of derivative. Now we have a slang version, and when we would say, what's a derivative, and I'll put that up here, when the question was, what is a derivative? And your answer was always slope of a tangent, SOAT. And then I would say, more specific? More specific? And your answer would change to formula. Formula for slope of a tangent. And then the next question would be, what does this represent anyway? And the answer was instantaneous rate of change. And then the question was, well, then what class are you in when you're doing average rate of change? And the answer to that would be not calculus, you'd be in an algebra-based class. So this right here, the slope of a secant, which was this formula, this is average rate of change. This is AROC. Slopes of secants. But slopes of tangents, I'm going to put that up front here, that's the formal definition of a derivative, but that is IROC. So these terms wind up becoming interchangeable. There's when you say a derivative, this is the formal definition of it. It's instantaneous rate of change. It's a slope of a tangent. It is the formal definition of derivative. Average rate of change, slope of a secant, you need an interval. You're just finding AROC, average rate of change. So for example on this one, you could say, well, what if my x-axis was equal to time? Okay, this is equal to time, and let's pretend that this axis was equal to distance, just to give you an example. So if we're doing time and distance, distance equals rate times time. You guys have known that ever since Algebra 1. Distance equals rate times time, and you would say, well, if you want to know the rate, you take your distance and you divide it by your time, and that gives you your rate. Well, it gives you your average rate. So for example, I like to say, what if you drive to San Diego, and that's 80 miles away? Okay, you drive 80 miles and it takes you 2 hours. How fast were you going? Or in other words, what was your rate? And you just say, oh, well, 80 divided by 2 is equal to 40 miles per hour. Well, you know that you didn't go 40 the whole time. You were speeding up and going probably 100, and then you got slow down with traffic, but on the average you did 40. But what we get to do, so this right here, this would have been this distance right here, this was your 2 hours. This was your 2 hours, and this distance of this bare velocity graph, but here would be our time, or our distance of 80 miles, and we would figure out our rate. Well, instantaneous rate of change would be like, okay, how fast were you going at the moment you passed the Shake Shack or something? Your interval is no interval. So the other example we did early in the year was, how fast does Usain Bolt run his 100 meters? Well, you could time him over the 100 meters, and he ran that in something, I don't know, can't remember what his speed is. Was it 9.3 seconds or something? You could divide his distance by his time and get his rate, but I want to know, how fast is he going at this moment in time, where the interval is 0 and the time is 0. And what we're winding up doing with IROC, whenever we do IROC, we have no distance and we have no time, and we have undefined statements. So we need to apply limits to figure out instantaneous rate of change, and that's the power of it all. Okay? This was just a brief little summary I wanted to go over with some limits and hopefully tying some things together. There is another way to do this, or another representation, just for some reason. If this comes up here, I'm going to adjust this. Sometimes they will do this. Ready? I'm going to make this A, and I'm going to make this B, and I'm going to make this f of A, and I'm going to make this f of B. And what they will do is, on all of these, this numerator would be f of B minus f of A, and this would be b minus a. And then down here, though, this is how it's be a little bit different. My numerator would be f of b minus f of a, and my denominator would be b minus a, but the limit statement would be the limit as b approaches a. Sometimes they'll write it that way. Everything else stays the same here. This example, sometimes you'd see that like in a multiple choice type question. Doubt it's going to be an issue for any FRQs, but just wanted to throw that out there. Okay, so we had a nice little limit review. This was just a little bit with the formal definition of derivative. And to give you an actual example for over here, let's just do something simple with the product rule. Let's say we had 2x cubed, and we wanted to find the derivative. We would say, well, by the power rule, that's going to be 6x squared. So back over to here, what's a derivative? It's the slope of the tangent. So this is equal to the slope of the tangent, but it's not really the slope, it's the formula for the slope. So I would have to give you a coordinate. So if I said, okay, what about at x is equal to 1? If x is equal to 1, then your slope here is equal to 6. So it's the slope of the tangent if I give you an x value. And what does that represent? Instantaneous rate of change, IROC. Okay, and so on the FRQs, sometimes they'll give you an interval and they'll want the average rate of change versus the IROC. Okay, a little bit of derivative review, and then I want to do one little thing with integrals. So the one little thing I wanted to go over with integration was just actually doing our questions here. So what is an integral? And some of this is on the review worksheet. And when the question is, what's an integral? The actual response is definite or indefinite. Definite or indefinite. And if it's definite, we would say, oh, well, definite is area under a curve. And we actually went over between two curves, but you're not going to need to know this for this test. And then what is it? If it's indefinite, it's going to be the formula for the area. Okay, and then the next question is, what does it represent? What does area under a curve represent? And the answer to that is whatever the function, which is usually a rate, is producing. And we've done that with the rate questions. So if we did a graph over here, and let's just contrast these really quick. So if we have the integral of f prime of x dx versus the integral of f prime of x from a to b dx, okay, we would say, well, the integral of this is equal to f of x plus c. And this would actually be the formula. It's going to be an equation. This, we're going to do the fundamental theorem, and we'd say, well, that's going to be f of a minus f of b. Oops. F of b minus f of a. Okay, and this is going to give us a number, and that number is going to equal the area. So if we did a very simple example, we're just going to do something very, very friendly here. We said, okay, what if we get, what's the integral of 2x plus 1 dx versus the integral of 2x plus 1 dx here? Well, if you integrate 2x plus 1 with just our basic integral rules, we add 1 to our exponent, divide by our new exponent, we're going to get x squared plus x plus c. We get the formula for the area under the curve, and on this one we get x squared plus x, but we're evaluating from 1 to 3, and we get 9 plus 3 minus 1 plus 1. So what do we get? 12 minus 2? And we get 10. We actually get the area under the curve. And in fact, if we were to graph this, which we could, 2x plus 1 is just linear, y-intercept of 1, slope of 2. And we were saying, what is the area under the curve from 1 to 3? Okay, that's actually what we were calculating. And we could verify it with geometry because I gave you something simple here. So this function was actually y is equal to 2x plus 1. Okay, so we could actually calculate this area, or this distance here. If we put 3 into there, 2 times 3 is 6 plus 1, that is 7. Put 1 into the function, we get 2 plus 1 is 3. Okay, or if we wanted, we could put our coordinate there, 1, 3. And this coordinate right here is 3, 7. And if we said, oh, well, the area of this trapezoid is equal to the average of 7 and 3, so that would be 7 plus 3 divided by 2, and our interval here is 2. 7 plus 3 is 10 divided by 2 is 5. 5 times 2 is equal to 10. Area under the curve, we got it both ways. Fundamental theorem versus area under the curve. And then we learned all of our more sophisticated ways of integrating all of that. But that was the basic. And the other really big thing we learned, super important, is that when you integrate a rate, because that's usually what these things are, if you integrate a rate from a to b, you are getting whatever the rate produces. And frequently, this is velocity. We integrate velocity, we get change in position. You integrate the rate you're putting bananas on a shelf, you'll get how many bananas you put on a shelf. You integrate the rate something's growing, you'll get how far it growed. That's a frequent thing they're doing. Okay, so just a little integration review, and you were applying all of these skills with all the FRQs. The only last little thing I'm going to do is if you get, just for example, if we integrate from 0, in fact, I'll pick another function. If I integrate from 0 to 5, and I'll do, let's do 3x squared plus 4x. Okay? 3x squared plus 4x. Well, actually, yeah, I'll go ahead and do this one. So if I were to integrate that, I would get x cubed plus 2x squared, and we would evaluate that from 0 to 5, and we would do that. But what I want to show you more generally is this. If you were to integrate from 0 to 5, and I'm just going to make this f of x, lowercase f of x dx, I would integrate that, I would get capital F of 5 minus capital F of 0, doing the fundamental theorem. Don't forget, we have those components that are happening, and frequently on these FRQs, you have to bring this over because they want to solve for f of 5. So we call it the initial condition. So just be prepared that you may have to just manipulate those and move them around. And that's come up several times. Okay. So just a little fundamental theorem here. And I guess the very last thing here is going to be, gone over this several times in the FRQs, the very last thing here is just going to be, I'm going to take the derivative of an integral. So I'm going to take d dt, and I'm going to do, let's say, 2 to t of f of x dx. Okay, a couple things going on here. This is the second fundamental theorem. And don't forget, when I retake the derivative of an integral, they cross each other out. But the big thing is, this variable has to match the interval. It's different than the integral. And so there's 4 pieces to this. I think this little arrow up here is referring to those. Remember, there's 4 pieces of this. This thing I stressed that your book doesn't put all 4 pieces. They only put 1. So the derivative kind of cancels that out. But I have to do the fundamental theorem here. And I have to do f of t times the derivative of t, which is 1, minus f of 2 times the derivative of 2, which is 0. And I've always stressed to you guys that there's 4 pieces going on here. But oftentimes these go to 0 if that's a constant, and if that's 1 if that's t. So the final answer here is just f of t. But you have to realize there was other things going on. Usually doesn't burn you. Might in a multiple choice, you probably won't have to worry about it. Okay, so just some light little integral review, hopefully stuff that you've had, or it's all just, it's come up frequently enough in the FRQ review that this was no big deal. Okay, so just a light little review. We did this before we started the FRQs. We kind of cruised through several things, but just in case you needed to see it again, there it is. All right, so keep reviewing. Good luck as you prepare. Thanks for watching. See you next time.